Sit down in a thinking chair and think.
So functions part 2 is some of the nitty-gritty stuff related to functions, overall basically composition of functions and inverses of those functions. Function composition is a very, very basic topic once you understand the notation. It's basically taking functions of other functions. So recall that we saw in the first video that if I wanted to evaluate f of, say, the number 2, I'll take that number 2 and plug it in for the values x all throughout this equation, and I get the output value f of 2. Well, 2 times 2 is 4, plus 3 is 7, so this would be the square root of 7. When x is 2, this function value is the square root of negative 7. Well, we're going to kind of extend that idea and just, instead of plugging in number values, plug in other functions. So this notation is read f composed with g, so that's this function f composed with this function g, and it's basically a shorthand notation for saying I'm taking f, and rather than putting x in, I'm putting this entire value g of x into this function. Well, I know what g of x is. The entire value g of x is x squared, so this is basically taking f of the value x squared. So what I'm going to do with that is go up to this function f, which takes x, multiplies it by 2, adds 3, and square roots all of that stuff. And instead of plugging in x, I'm plugging in x squared. So everywhere I see an x, I'm replacing it with an x squared plus 3. So there is my value of f composed with g. You can also compose things in the other direction. And what's interesting is that this composition gives me a completely different output than this composition. So this is really g of the function f at x. So I'm going to take the function g and plug the function f of x into it, which means I'm taking the function g and plugging in the value for f of x, which is this entire square root expression. So it would be the square root of 2x plus 3, which is equal to, well, this function g takes whatever my input is and squares it. So it's taking this entire input, the square root of 2x plus 3, and squaring it. Well, since squares and square roots are inverse operations, they'll undo each other, and it leaves me with just 2x plus 3. A very different result than the composition in the other direction. Now, after we looked at compositions, we looked at some special type of functions called inverse functions, which are basically functions which undo their original function. An inverse undoes whatever the original function does. So mathematically, when I compose those two functions, I get back exactly what the input is. So the net effect is nothing. It takes f inverse takes x, does something to it, and then f undoes that and gives me back the original value. It's also true when I compose it in the other direction. And this gives me a way for verifying, this definition of inverse functions gives me a way for verifying whether a set of functions are in fact inverses. So in order to verify a set of functions are inverses, I need to do both of these compositions, and if both compositions give me back the value x, the functions are then inverses. So here's an example of that. Verify the following functions are inverses. So I need to look at the composition of these two functions in both directions. So that what I mean by that is f composed with f inverse of x, find out what that is equal to, and then I also need to compose this in the other direction, so f inverse composed with f. And my goal is to show that these are both x. Well, let's plug these values in. What this composition reads is I'm taking the entire value of f inverse, that's all of this stuff, and plugging it in for x here. So that's all of that stuff, which is the cube root of x minus 5. That's f inverse, and I'm plugging that in for the x value here. So I'm replacing x with this. So it will be all of this stuff cubed plus 5. Well, cube root and cube undo each other. So I'm left with x minus 5 from that first term, plus 5, and negative 5 and plus 5 cancel out, and I get x. So far so good. The composition in this direction gives me back x, so let's do it in the other direction and see if that gives me back x as well. So this time I'm taking the f of x value, which is x cubed plus 5, and I'm plugging that stuff in for x in this expression. So it'll be all of that stuff minus 5 cube rooted. Okay, well, positive 5 minus 5 cancel out. That gives me cube root of x cubed, which again, inverse operations of each other. So I get x. So since composition in both directions give me back x, these are inverses. So I say, therefore, these are inverses of each other. That is how you verify a set of functions are inverses of each other, using that definition of inverse, that the functions undo each other and give you back the original input. So there's a couple properties, or actually, that's verifying inverse functions, but you also need to be aware of how to find an inverse function. We went over two methods. There's a shortcut method, which is the informal method, and then there's a slightly longer method algebraically when we're not able to do it informally. So when you are easily able to, or there's only, if you have a function where there is only one variable, x, you can do the inverse informally. When you have an expression where there's more than one occurrence of that variable, like the second case, I have x in 2 locations, I'm not going to be able to solve it informally. So that's how you decide which method you'd want to use. So let's see what these methods, or let's remind ourselves what these methods are actually like. Okay, so here I have g of x. I'm going to list what basically happens to x. So pretend you're this variable. You're going to list all the things that are occurring to you in order. So from x's perspective, the first thing that's getting done is it's getting squared. So I'm going to write x gets squared. Then this is now the expression I'm talking about, x squared. It's multiplied by -5, so I have times -5. Then that whole expression is added, 6 is added to that whole expression. So plus 6, and then that entire expression is divided by 7. So if you remember, we used the example of socks and shoes to figure out how to figure out what the inverse function is. When you put on your socks and then your shoes, the inverse operation of that would be taking off first your shoes and then taking off your socks. So to figure out what the inverse is, the function did things in this order. The inverse is going to go back. So I'm going to have to undo these things in the opposite order. So the first thing my inverse function will do is, rather than divide by 7, is multiply by 7, which is here. Then it will subtract 6, so I'm basically undoing these things in the reverse order. Then I multiply by -5, so now I'll divide by -5, and then I squared it, so I will square root it. So let's write this out. The inverse function g will take the value x, multiply it by 7, subtract 6, divide by -5, and square root everything. Okay, so that is my inverse function. Now, if this method seems confusing, you can always fall back on this algebraic way of solving, and it's slightly different. So let's go through that method. The algebraic way of solving for the inverse is, I'm first going to simplify this. Rather than using function notation, I'm going to fall back on my old graphic notation. So y equals x plus 3 over x minus 2. My first step is to interchange my x and y values. So I'm going to rewrite this as x equals y plus 3 over y minus 2. And now, this y in this new expression that I've just written represents the y value of the inverse function. So I need to solve for that y value in order to know what my inverse is. So the first thing I'm going to do is multiply both sides by y minus 2. And I get x times y minus 2 equals y plus 3. I'll distribute my x. I get xy minus 2x equals y plus 3. And if I'm solving for y, I'm going to need to isolate all these expressions with y to one side in order to solve for it. So let's continue this process over here. So I'm going to subtract y from both sides and add 2x. So I'll write that down. I'm subtracting y from both sides, and I'm adding 2x to both sides in order to get my y's to one side and everything else to the other. So that will give me xy minus y is equal to, oops, sorry, this was supposed to be an x, 2x to both sides, 2x plus 3. Well, now your question might be, well, how do I get y by itself? Because it's here with an x. Well, since y is a common factor of these two terms, we can factor that out, and I'm left with x minus 1 equals 2x plus 3. And now if I want y, I'll just divide both sides by x minus 1. And I get y equals 2x plus 3 divided by x minus 1. So now that I have this y isolated, that was representing my inverse function. So h inverse of x is equal to 2x plus 3 divided by x minus 1. So that's the algebraic process. Now if you wanted to, you can use this same process to solve for the inverse in G over here. It's just going to take slightly longer than doing it informally. If you get good with this informal process, it actually speeds up the process for solving the inverse quite a bit. Okay, the last thing we need to talk about is some properties of inverse functions. The main one is that any inverse function and its original function are symmetric over this line y equals x. Okay, so here's the graph of f, which is 1/5 x minus 4 cubed plus 2. So that's this blue graph here. Its inverse function here, which you can solve for by using either of the two methods we just discussed, when graphed looks like this. Well, these two lines are symmetric over this line y equals x, meaning that every point on the graph of f has a corresponding point through this line of symmetry on the graph of its inverse. This has an interesting effect on the domain and range of functions, and it also gives us a way for testing whether or not a function has an inverse without actually having to find its inverse. So I'm going to zoom out for a second, and I'm going to remind us of the horizontal line test for functions. We'll recall from functions part 1 that we have a vertical line test to see if something is a function. Well, I'm going to look at, say this red graph here represents my function, and this blue graph represents its inverse, since they are symmetric across this line y equals x. I'm going to take a look at my graph. Now, I can, as I drag this vertical line through my graph, I can see that it is actually a function. For every point along this line, there is only one point on the graph itself, but as I zoom this out to look at what happens with my corresponding inverse, notice that my inverse, the inverse of this graph, is not a function because this vertical line is intercepting it at more than one point. Well, the main thing that I want to point out about this line of symmetry is that notice I have a horizontal line here that corresponds to this vertical line, and as I drag these along, I have 2 points on my inverse graph have these 2 corresponding points on my original graph. So if I wanted to determine from based on just looking at my original graph if it has an inverse, I can use a horizontal line test. And if a horizontal line intercepts that graph at more than one point, the vertical line on its inverse would intercept at more than one point, meaning its inverse is not a function. So we have a horizontal line test for testing whether or not something has an inverse, testing whether or not a function has an inverse function. So if it does not pass a horizontal line test, its inverse will not be a function. Okay. Now, notice for these particular graphs, the parent function for this graph here is the x squared, the quadratic function. So the parent function would look like this. It's just been shifted up. Now, we know that the squaring function has its inverse is the square root function, but recall that the square root function is actually just this upper half of this graph. So I can make this function have an inverse if I restrict its domain. Now the reflection of this, when reflected, will look somewhat like this. And what actually happens is that we can restrict domains to make something pass a horizontal line test. So if I'm only looking at the highlighted parts that I've just highlighted, those graphs would be inverses of each other, and they are in fact inverse functions. Now it has an interesting outcome when we look at the domain and ranges of these graphs. So now let's look at what the effect on the domain and range is. Notice here it says the domain and range interchange, and let's see exactly why. Well, these two functions represent the two functions I just highlighted. So this thick red line and this thick red line. This is, actually let me do them in two different colors so that you could see them a little bit more clearly. I'll do this in a thick blue line. So the thick blue line represents my square root function. That's my original graph here. The thick red line representing its inverse is this graph here. So there we go. Let's look at the domain. The domain of this blue line, it's starting here at the x value equals 3 and continues on for infinity. So that will be from 3 up to infinity is its domain, and its range, its output value, is starting here at 0, and the part I highlighted starts at 0 and continues up for infinity. So it's going to be from 0 to infinity. The domain and range of the red portion I highlighted, well, that's from here and continuing the positive direction for x. So x is from 0 to infinity, and the output value for y is from here and up, which is from 3 to infinity. So when I say that the domain and the range of the inverse and its function interchange, I mean that the domain of my original function has become the range of my inverse, and the range of my original function has become the domain of my inverse. So domain values and range value interchange for these inverse graphs.